Like, what is binary search? So like it is mainly a searching algorithm which searches a particular key element in order of log in time and with a space complexity of order of 1. So for this, the binary search, the condition should be like the array should be in the sorted order, the first main case. If the array is not sorted, we can't apply the binary search algorithm. Although we apply the binary search algorithm, we may face difficulties in finding our key element, and the loop will be like forever in the loop and we won't find the required answer for it. And so let us discuss the first case. So array is 1 2 3 4 5 and the key is 4. So in the first iteration, what we do is the binary search is all about how we reduce the search space. So that in first iteration, we'll place 2 pointers, left pointer and a right pointer. Left will be marking to our first index and the right will be pointing to our last index. And now we'll calculate a mid element or mid index, which is left plus right by 2, that is 2. We'll check whether the key is greater than array of mid or not. So like if the key is greater than array of mid, then that means we'll probably find our element after the mid element because the array is sorted. So what we can do is we can simply update our left to mid plus 1. And in the second iteration, the left becomes the 3, which was mid plus 1, that is 3, and the right will be the same, 4, and the mid will be now 3 plus 4 by 2, which is 3. And now we can see that keys is equals to array of mid, that is 3 is equals to 3. So like 4 is equals to 3. So then we can say that we can return our mid. So in our case 2, like we have the key element as 1, and in the first iteration we have our left pointed to 0 and right pointed to 4 as in the previous case. So now mid will be 2 and the key element is less than the array of mid. So what we can do, we can simply right is equals to mid minus 1. We are reducing our search space here, that's it. So our second iteration will be left equals to 0 and our right is equals to minus 1, which is mid minus 1. And now our keys is equals to array of mid. Yes, that's true. So we'll return mid. And what is our case 3? Like array will be the same and the element is 2. Left is equals to 0, right is equals to 4 and the mid will be 2. And now here the key and the array of mid are equal. So what we do, we return mid. What if the element is not present in the array itself? So like we can simply return minus 1. So let us discuss about the time complexity of the algorithm. So probably what we are doing is at every iteration we are decreasing our search space by half. So like n is converted to n by 2 and n by 4 and n by 10 and so on. It goes until 0. So total height will be probably equals to log n with a base 2. So each step we are just calculating mid, which takes a constant time. So each step total takes order of n and each step takes order of 1, which is order of n plus constant time, which is probably equals to order of n. Space complexity will be like we are only declaring 3 variables like mid, left and right, which is order of 1, order of 1, order of 1. So they are probably equals to order of 1. So let us write the algorithm code, and this is a constants I declared. So the array is this one and we are searching for 100 here. So what we can do is we can simply place our left pointer, which is pointing to 0, and right is pointing to array dot length minus 1. And now we can start a loop where left is less than or equals to right, because whenever the left exceeds the right, that means we have traversed the entire array and we are not able to find any element. And now let us calculate mid, and we can use our parseInt function here, so that we'll be getting a round off here. And yeah, and like now we can check that whether our key is equals to array of mid or not. If that is equal, then we can simply return our mid index. Else if our key element is less than array of mid, then that means the key should be searched in our left search space. So what we can do, we can simply update our right to mid minus 1. And what if it is less than? So we can simply update our left workspace to mid plus 1. What if we are unable to find the element? Like whenever the loop exceeds, that means we are unable to find the element. So we can simply return minus 1. And let me save it and let us run this one. And we can run this one and we are getting a small error here. Okay, like I have mentioned here start and end, and we can change to right here, and probably this should work. And we are getting minus 1 because 100 is not present in our array. So So what happens is, like, let me change the key element 1 here, and let us run the code again, and now the index is 0. So yeah, I think you probably understood about the binary search algorithm, how we write in JavaScript. And let me discuss another way which increases the efficiency of binary search. So we know that binary search is already an efficient algorithm, but why do we need another efficient algorithm? Actually, it's not efficient. Like, it is probably an error-free thing which we can do in binary search. So like, what if the size of array is too large? Like, let us consider a key which is present at n-2 index. So that means the last second index of the array. So at this point, the left will be probably, at some point it will be n-2, and your right will be n-1. So like, we are making here, like, mid is equals to %, and left plus right by 2, which means we are adding n-1 plus n-2. So that means you are adding a large number to another large number. So this should probably exceed the integer limits, right? So that will raise an error. So here comes our problem. But how can we overcome it? So like, this will be our savior formula here. So like, instead of writing left plus right by 2, we can simply write as left plus right minus left by 2. In this way, what we can do is, we are reducing the integer overflow here. So like, by doing this, we are adding n-2, which was left, plus n-1, which is right, minus n-2, that is which is left, and probably we are just adding n-2 plus 0, which stays under the limit of integer range, right? So this is an error-free algorithm when compared to the before binary search. So what we can do is, we can simply modify what we had done here. So we can make as left plus, and we can make it as here right, and probably minus right, minus, and left. This will probably fix our issue, and it works as same. Like, there is no change in our algorithm, so it works as same as this one. So we can place some other number, and we probably the same answer. So I think this approach is better when compared to the previous approach which we followed directly by left plus right by 2. I think you enjoyed a little bit and learned more about binary search in this session. So